Hello and welcome to another Solana tutorial. This episode is gonna be a good one because I've been waiting to make this video for a while. Today we're finally gonna talk about Transaction V1. That's been on my list for a long time. Since I heard about it first, that there will be a new standard, I was like, I need to look at that. And today is that day where I will look at that together with you. We're gonna do a deep dive on Transaction V1. Because I love it if stuff is changing and we get to build bigger transactions. But maybe to step back a little bit here and to get everyone on board on what this really is, it's not that Solana has different types of transactions. On the cluster, they're all just transactions that are being executed. It's not like one transaction can call those programs and then the other version of the transaction can call other programs, or that a certain version gets more priority or anything like that. That's not what this is. On the execution levels, transactions are treated the same. All of them have instructions that call programs. The difference really is just in the wire format. In the serialization from your client on the way to the validator. So what you're sending from here to the RPC to the validator. That format has different versions. And we started with legacy. Well, when we started, it was just this one format that we now call legacy because it doesn't have a version. But you can do everything with a legacy transaction. For most use cases, a legacy transaction is just fine. You can put instructions in there and the block hash, the fee payer, you add some signers, bam, that's all you need for a transaction. But then they start with version transactions. So they did a little hack with the uppermost bit of the first byte, and if that is set, then it's a version transaction. We talked about this when we talked about transaction v0, and yes, they start with 0. The first version transaction was version 0. Those are the ones that existed so far. And now, soon, they will release version 1 transactions. And those are the ones that we're going to have a look at today. V0 transactions added lookup tables because those were needed to get more accounts into one transaction. So for a specific use case, you wanted to use V0 transactions because you can't do account lookup tables with legacy transactions. And the same is going to be true for V1 transactions. For specific use cases, you want to use V1, but for other stuff, legacy will just be fine. We're gonna have a look at that in detail today. So today, we're gonna look at the SIMD and check out the specification of V1 transactions. Then we're gonna send our first V1 transaction. And then I wanna dissect it really, because I like to do deep dives. I wanna see it on the byte level. And in the end, we're gonna discuss when you should use a V1 transaction and when they're coming out and all that stuff. So, a lot of things to do. Let's get started. Okay, I found the relevant documents. So there is SIMD 296, larger transaction size, which basically talks about currently transactions are limited by the MTU size, and therefore the actual transaction size only has 1232 bytes at most. But since we're now using Quick, that limit could be increased, and that proposal suggested 4 kilobytes. So one motivation was to do bigger transactions for reasons that you can read up on if you want to. And here it says all of these changes are implemented with a V1 transaction format, and it's not touching V0 or legacy. So it will get the same feature gate as the one from transaction V1. So the really interesting document is this one, the SIMD 385, which again, this document is stale. It says it's under review and doesn't have a feature gate yet. Although maybe I'm just looking at an old version of this document. Let me just quickly double check. Oh, that's in Jacob's, hold on, from Solana Foundation Solana improvement documents. Here, what do we say? 385 transaction V1. No, also here it says under review and feature gate not known yet. And that's just a thing that happens. Those SIMD documents, once they reach proposal state, they don't always get updated. But I know for a fact that there is a feature gate for this because I have seen it. Just making sure that I am on the newest. I am. And starting a test validator and then Solana feature status. I've been writing that a bunch lately. Here it is. So I know that this feature gate exists. It even got rekeyed to TXV1 something something something. So that's a thing. It's already in validator code. I don't think it's active on any of the clusters yet. Let's check that. It's certainly not active on mainnet, also not on devnet, but the account exists on all of them. Like even on mainnet, this account exists, right? We can look at that raw and we see that it has 0 bytes. So it's not activated. If it would be activated, then it would have a 1. You can see any other feature that we know got activated. For instance, the one we talked about yesterday, the reduced slot times feature gate here. Look, this one is active on mainnet. And if we look at that raw, then here's the one indicating that this feature is active. And what those 8 bytes mean, I actually don't know. We could talk about that when we do a FeatureGate program deep dive. Not today's video though. Today we talk about transactions in version 1. So why this and what's that about? Currently we have V0 and legacy transactions, as I mentioned, and they have a number of limitations. And this proposal presents a new transaction format that is designed to get rid of the need for the compute budget instructions. Yes, because that is a thing that is annoying. There's that compute budget program that you need to put in as an account and then call an instruction that is a no-op instruction, but you pay for the instruction anyway. That was basically a hack such that we can make legacy transactions add priority fees and stuff with no-op instructions to the compute budget program. But if you would have designed that from the beginning, which they didn't, for obvious reasons, first you want to get it out and then you want to make improvements. If you would design it now from scratch, then you obviously would do the requested compute and the priority fee as arguments in the transaction directly, because that's more efficient. So if we have a new transaction format, then we can do it more efficiently. The result will still be the same on the validator. The validator will interpret that and then put the right values. But this one is more efficient because we don't need to add extra accounts. And also don't waste compute on an instruction that we don't need. We also get rid of address lookup tables. See, address lookup tables were introduced in V0 because legacy transactions couldn't add enough accounts. But with the total transaction size going up, you can just put more accounts into that transaction directly, so you don't need account lookup tables anymore. And that's already important to note. V1 transactions will not have account lookup tables. You cannot do ALTs with V1. That's a design choice. Because also ALTs, you could argue, are somewhat inefficient. And more to speed up transaction ingestion and processing. So with those improvements, it's better for the validators, basically is what they're saying. They can work more efficiently. And it's also good for you as devs because it's more efficient to request the right resources, and therefore you don't waste CUs and other resources, and therefore you need to pay less in priority. So good for everyone. Yeah, so it saves the developers space in their transaction by including compute budget information in the transaction header. This is going to be one of the biggest changes for us. And the funny thing is, really, you as a dev, you don't even need to worry much about it. You need to worry a little bit about it, admittedly, but you don't need to worry much. We'll see that when you work with the kit. Okay, detailed design. This is where it gets interesting now. So, the new transaction format is proposed to enable larger transaction sizes. And that's what it looks like in bytes, right? That's what we serialize it to. First byte, the version byte. You know this one from version 0. In version 0, it was just the uppermost bit set and the rest 0 for version 0. So that was 128. And now it's going to be the uppermost bit set and then the lowermost bit set for 1. So it's going to be 129, this byte. Then comes the legacy header. That's the one we know. Writable signers. I always mix that up because it's not intuitive for me. Read-only signers and read-only non-signers, right? I think that was in that header. And then number of addresses, which came after that in the other transactions, is now here. So that got moved down. It's not the next byte, but the next byte is a U32. So that's actually 4 bytes with a bit mask of which config requests are present. Okay, so individual bits of those 4 bytes you can set to 1, indicating that this config value you are setting. And the amount of ones in those 4 bytes will define the length of this array here. So each of the configs is then actually a 4 byte number as well. So another U32. Okay, and what config values there actually are, we'll have a look at that. The lifetime specifier, that's the block hash or the durable nonce. Block hash, durable nonce, the over term for that is lifetime specifier. Other transaction formats probably called it block hash and then put the nonce into the block hash. And durable nonces will change anyway, but as long as they still work, that's where you put them. But in most cases, this will just be the block hash. 32 bytes. Then number of instructions. Interesting. This is now also taken out and it's not directly in front of the actual instructions. Most likely because that way you can parse transactions quicker, because now that byte will always be in that place in the transaction. So this one will always be the 1, 2, 3, 4, 8, 40, 41st byte. So in every V1 transaction, if you just check the 41st byte, then you get the number of instructions. That isn't true for V0 or legacy transactions, because there it depends on how many addresses are there, because it's first all the addresses and then the array of instructions first had the length of that array, but you still need to parse the individual things to get to the number of instructions. So if you just want to have the number of instructions of a transaction to make a quick decision, does it go there, does it go there, whatever, I don't know what validators actually do, but I imagine something like that, then this is more efficient. So that's most likely why they put it out. And the same with the addresses, but the number of addresses is actually directly before the actual addresses. But yeah, it used to be like right here. Yeah, cool. So yeah, each address is 32 bytes. We know that. So it's just the array of addresses. Then come all the config values. We'll see that in details later. And then come the instructions, which of course must match the number of these. But here they also did something interesting. Instruction headers and instruction payloads. Probably for the exact same reason, they are now switching headers and the payload such that for the headers you have an exact offset. So you can say, give me the headers of the 4th instruction, then you can immediately jump there. Whereas if it would be headers and payload, then you would need to check each previous payload, how big it is, and then jump over each of them. So yeah, like that, it is more efficient to work with, not to pack. It's not packing efficiency. That's the same if you would put the payload right after. It's not that we need more bytes. But we have also seen that, like, very early, I already talked about this when we were writing our first Solana programs, when we were packing accounts and writing the data layout of our program accounts, you know, our PDAs or whatever. I always said, put the variable length stuff in the back, such that the fixed length stuff you have on top, so you can quickly access that and you don't need to parse the entire account for it. And the same thing is happening here. All of that is fixed length. Then we get variable length, but with fixed size. So if we just know that, then we can quickly jump over all of the addresses. And if we know the bit mask here, then we can jump over all of those. So that's also cheap to jump over. The only thing where it actually gets more expensive is here with the instruction payload, because even though the length of that array we also know from the number of instructions, but how big each payload is different per instruction. Therefore, put that in the very back here. So the payload is a concentration of the following byte arrays, the instruction account indices, so which accounts from here the instruction references, and the instruction data, and the length for that it gets actually from the number of instruction data bytes, which is in the header. It's a U16 in the header, along with the program that instruction actually calls and the number of accounts this instruction calls. So this one that gives the length for that, and this one gives the length for that. But that's in the header, and the actual data comes after, just for efficiency, not for making it easy to read if you have the bytes. More easy to read for a computer. So that's the transaction message, right? It has all the things, a block hash, the fee payer. It also specifies the fee payer indirectly, I assume the same way that all the other transactions did it, with the first address in the list of addresses, because the first addresses will be the writable signers, and the very first writable signer is the fee payer. That's just Solana convention, so they will do it the same here in V1. So block hash, fee payer, and instructions with their instruction data and accounts. It's all there. That's how you build a transaction message. And with V1, we can even config stuff properly through this mask and those values. Great. So message, and then signers. This one I'm now actually curious about, because if I remember correctly, the signers used to be before the entire transaction message, but that would be weird, because then you're not checking the same first byte anymore. Maybe it was also serialized after. But for some reason in my head, the signers in a wire transaction are first, and then comes the transaction message header. Maybe I misremember that. But here with this specification, it kind of looks like all of the signers, and you know how many those are by just adding those two numbers together. So the signatures, sorry, not the signers. The signatures, the signers are in the addresses signing, but the signatures provided for the signers, they are here. A signature is 64 bytes, yes, and add those together to get the number of signatures. And it kind of sounds like that's just at the very end of the transaction. We're gonna double check that, because that would honestly be weird, because then to get to the signatures, which is an important thing for SIG verify, to even check if a transaction is valid, you would need to parse through all of that to get the offset right. I almost can't believe that's how they're gonna do it. So this is an open question. Where do the signatures live? Anyway, let's keep scrolling. Version byte, yep, 129. I said that. Legacy header is unchanged. Number of required signatures. Oh, I got it wrong. Number of required signatures is the first one. Then number of read-only signers. And then number of read-only non-signers. Right, I got that wrong. Sorry, my bad. You don't need to calculate those two together. It's just this one, the total number of signers. And if you want to have the writable signers, you subtract the non-writable signers. Yeah, more efficient to get all the signers. You don't need to do an addition. That's why that number is actually the total number of signers. I know, that header always, like, I usually got that wrong, but it's written here. Number of signers, then number of read-only signers, then number of read-only non-signers. Okay. Number of instructions is set to the number of instructions in the transaction. So 64, that is a limit that the specification gives us. It's not the limit of how many we could actually pack, because we have 4 kilobytes now, but in order to change that, there would need to be a change through a SIMD and another feature gate. So for now, in the beginning, we also just allow 64 accounts. Do I want to go through all of this? There's also no padding between each 4-byte element, because we don't want to waste bytes. No padding in the transaction, please. Okay, yeah, I read through this. There's nothing that I got wrong. Let's check here, maybe we get smarter here. Signatures, an array with number of required signatures, each consisting of the ED25519 signature, and signature I corresponds to addresses I. That also makes sense. That's how I explain it as well. Transaction must not contain trailing data after the signatures field. There are no padding fields. But that also sounds like the signatures are in the very end of the transaction, which just seems super weird to me. Anyway, the new V1 transaction format notably does not include address lookup tables. We said that before, we say it again. No lookup tables, because in V1 there was an entire array for lookup tables. Okay, now to the interesting part. That's a cool table as well. So the transaction size would be 4 kilobytes. Previously, it was that, and 4 kilobytes is also the maximum we can do with that format. Signatures per transactions are 12, defined by the SIMD. We don't allow more signatures than we previously allowed, because all of that would be a different discussion. Here we're just introducing a new wire format that could theoretically allow up to 42 signatures. But we stick to 12 and have the discussion if we want to allow more in a different proposal. And the same with the number of accounts. It would theoretically support 96, but for now we stay with 64. And also the number of instructions. It could do more. Why 255? Those, I think, are limited by transaction size. Yeah, that roughly checks out because 32 times 96 is roughly 3,000 plus the rest of the overhead that will hit the transaction size soon. So I think those are given by the actual size capacity. This one is given by the number format used for encoding the number of instructions, 255, because we just use 1 byte for the number of instructions. And the same with accounts per instruction. It's also just 1 byte, therefore that's the limit. And if you now argue, well, but an instruction needs at least 1 address for the program that you call, yeah, but it can always be the same address, so you just need to put it in there once and then reference it, and that just costs 1 byte. So yeah, that would be pretty, you could pack instructions pretty efficiently to easily get to the 255. Anyway, that's just the theoretical limit, and the theoretical limit is also allowed for accounts per instruction. We can actually put 255 accounts in one instruction. How would that work if we just allow 64 accounts? Well, an instruction can take the same account twice. For instance, you provide it as the authority and then also as the payer. Same account, but it's just a 1 byte reference. Okay, good. But now, finally, to the thing that I am most interested in because it's new. This is the new stuff. The new and shiny transaction config mask. What configs do we actually put in a V1 transaction? I have not looked at this yet. That's why this is exciting. It's intended to be flexible enough to add new fields in the future, and is initially aimed at replacing the compute budget program instructions that are currently used to configure transactions. Each bit in a mask represents 4 bytes in the config request array. We saw that up there. And if a config value such as priority fee needs more than 4 bytes, the field can use 2 bits in the mask. Okay, that makes sense. So you fine grain it by 4 bytes because some things just need 4 bytes. And if something needs more than 4 bytes, because that's a U32. Most configuration things will probably just need a U32. But priority fee is Lampert's, and Lampert's is a U64. So you just use 2 bits of the mask. Wait, how many bytes? We have 4 bytes, which means 4 times 8. No, don't use the calculator for that. I should have been able to do that myself. So 32 U32s we could put in there. So there are 32 fields for a config, or 16 if all of them would need 2 bits. Okay, good to know. Initially, we just used the first 5 bits to provide the first 5 U32 values, or rather 1 U64 and 3 U32s. For priority fee, 8 bytes, compute limit, 4 bytes. So those are the 2 classic compute budget program instructions, the set priority fee Lampert's and the set compute unit limit. This is how many compute we request, and this is how much we pay for it. And then the requested loaded account data size limit, we also had a look at that in a previous video. That's another compute budget program instruction. And then you can also request the heap size. I don't think I ever did that in a video, but that's also, as far as I know, currently done with a compute budget program. And those things you can specify in the V1. They might change the V1 transaction format later and allow more bits, but for now that's what we have. Okay, obviously for 2-bit fields, both of them must be set. If only one is set, then the transaction is invalid. Okay, yeah, that sounds very fair. And for transaction V1 transactions, any compute budget instructions are ignored, even if they're invalid. Okay, and that's a good thing to know for us as devs, because since all of the compute budget program instructions are ignored anyway, you don't want to put compute budget instructions into your V1 transaction, because then you just pay for the 150 compute of that instruction invocation that does nothing and changes nothing. So don't do it. Don't put compute budget program instructions into your V1 transactions. That's the one takeaway. Because for the other things, they're gonna be automatically handled by the kit anyway. And also this, I think, is gonna be handled by the kit anyway. We'll see that in a second. Okay, for the cost model, all transactions are treated as if requests are present. For all fields, if the bits are not set, the minimum allowed value is used. That's also interesting. So if you don't set those bits, then the minimum is used, not the default value, because with legacy and v0 transactions, if you don't do compute budget program instructions, you get 200,000 compute units per instruction. But for the minimum allowed value is used, and the minimum allowed value is usually 0. 0 for priority fee, 0 for compute unit limit. And you don't want to have 0 as your compute unit limit, just saying, because I mean, then you can literally compute nothing and your transaction will immediately fail. So yeah, you better set a value there, I guess. I mean, that kind of forces you that you have to set something there, which is an interesting decision as well, because in a way it blows up that transaction because you will have to set that value, because otherwise it's 0 and it's gonna not work. But in a way it's also good because it forces devs to set an appropriate number and not go with the default that is way too high. And if we would do a lower default, then some devs would be like, wait, why is this there? So putting it to 0 is probably actually a good strategy, because then you really need to set it. So you will need to think about how much compute you request. Or you're like, whatever, I request way too much, like most people will probably. But yeah, if this one is not set, the data size is 0, and probably also that is not ideal. This is different to the current requested accounts data size limit defaulting to 64 megabytes, which is the max loaded accounts data size bytes. And if we have a 0, then it's treated for cost model purposes as reserving 1 page of loaded account data. So that's a note that the cost model will still charge you something even though you're not getting it. It's basically what that's saying, I think. Maybe to avoid that you can cheaply get yourself in there and then fail anyway. Yeah, something like that. I don't know. If bit 4 is not set, the heap size is 32 kilobyte, which is the min heap frame bytes. Okay, so there we actually get 32 kilobytes though, because we will need some heap. But 0 for account data size is actually fine. That account data size, however, is just the data parts of the accounts, right? We don't count the LAN ports and stuff as data size. I would need to double check that. I'm not sure. But I think if you have just accounts with data length 0, then it's fine if you request 0, because otherwise that just wouldn't make sense, because you couldn't load any accounts. So I think 0 is fine for this one. And the heap size must be a multiple of 1 kilobyte in this range. Otherwise, your transaction phase. Okay, good, we went through it. And as developers will adopt this new transaction format, validator clients accepting their transactions will be much more efficient at ingestion. And that's what we want, right? We want the validators to be more efficient. So even though I said in the beginning, it doesn't really matter, you can still use legacy transactions. It's probably good for the network if you were to use V1 transactions. Not true for V0 transactions. They actually add overhead because of those lookup tables. And one last time, because we haven't said it enough, no more lookup tables, which are commonly used in the developer community today. So this is actually then probably the biggest change for you devs, because if you're using those, you can now not anymore. Okay, no security considerations at this time. Good, we looked at the SIMD. It took a while. Now let's finally send our first version 1 transaction. Good old template. We are going to get us the Solana kit in the newest version, which will be version 8. Great. And what are we going to do? We get a few instructions. Get transfer sol. Let's also pnpmi Solana program system and compute budget, because we will need them for now. And then we get a transfer sol instruction. Nothing special. I just send to a random address. And for that not to fail, I need to put minimum balance for rent exemption for a 0 byte account. Okay, so just a sol transfer. Then we get a block hash, set fee payer, set block hash. That's the transactions we have in there. And we're gonna look at how to do it properly later. Let's do it the old school way with get Set compute unit limit instruction. I'm doing 150 here, 150 here, so I request 300 to be exact and efficient. And that's absolutely nothing new. We have done this 1,000 times before, even with legacy, but I'm gonna tap in here and check what's on the wire, log myself the wire bytes, and then I send it anyway. Let's do it. So npx tsx transaction v0, which is actually, we said it's a legacy transaction. Let me rename that. Let's do legacy. Right. Oh, we are getting a base 64 encoded wire transaction. Dang it. 1 second. So this is the wire transaction. So let's get a base 64 codec and encode. Yeah, return the bytes. That's what I want from this wire transaction. I want to see the bytes because I can't read base 64 and I need to save my files. There we go. So number one, I don't think I misremembered. In a legacy transaction, the signatures actually do come first. That's 64 bytes, right? No. So that's 12, 24, 48, 60, 1, 2, 3, 4. Here. That's the signature. There's one signature, that's the signature, and then comes the header, which is this actually. There is one signer, 0 read-only signers, 2 read-only accounts, system program and the receiver, and there are 4 accounts in total. No, the receiver is writable, that's not here, but the compute budget program, that's the second one. Okay, so that makes sense. That's the old way of doing things, right? That's the legacy way, and we don't need to check the rest. We did that in previous videos. Let's do the same, but with a version 0 transaction, then it looks slightly different. We still have the signature first here, and then the 128 indicating this is a version transaction version 0, and then the same header. So there's this one additional byte. All right, so far so good, because now guess what? The kit already also supports version 1. So let's do version 1. This will fail for several reasons. Most prominently that DevNet doesn't support version 1 transactions, but let's see what happens. My question is, do we die before or after sending the transaction? In the simulation, transformer error. There, cause Solana error, transaction version is unsupported. Yeah, okay, that's even a very speaking error, verbose, as you say, a very verbose error. It tells us exactly what's the issue. This transaction is not supported. But before we sent it, we still got that. And look at it, really, they are really putting the header first. Wow. Okay. That means 2 things. Number 1, the version is now at a completely different place, meaning the first byte, which makes it also more quickly to decode and select, which is actually great. So you don't need to check how many signatures there are and skip that many bytes to get to that header and see what version it even is. The reason why this still works is that there can never be more than 127 signatures anyway. That was already the exact same reason, the exact same strategy that they used when they decided, hey, we're just gonna, check that first byte because that must be smaller than 128 anyway, because it's the number of total signatures and our transactions don't support so many signatures, so we can just use the uppermost byte as a flag. And the same thing is now happening here, just that the validators now need to also check it here. If the number of signatures happens to be 129 or bigger for future versions, then this is not actually the signature. It's a different transaction version. It's version 1 of the transaction. And so we need to check that stuff first. And the signatures are actually in the very back, which is still kind of weird to me because I thought sig verify would be one of the early steps of a transaction, because now it's way more complicated to get to the actual signatures of a V1 transaction because it's at the very end. But yeah, cool. It still seems overall to be more efficient like that. That's why they changed it to that. So yeah, that's very interesting. Very interesting. We see version, first byte. The checking now goes like this. Is it smaller than 128? Then it's the number of signatures. If it's bigger, it's the transaction version. It's already the transaction version, the first byte of the header. Oh, wait, hold on. Wait, that makes so much sense now. I just had it click because earlier in our previous transactions, this number is in their double anyway. This one also is this one, and it must be. This one must be equal to this one. This one provides the length of the array of signatures, and this one is the header of the transaction message saying how many signers there are, which obviously need to be the same. So this is a byte that you could save yourself. Interesting. And they put the signatures to the very back to have those things, right? Those values at the same points always, at the same places in the transaction. We'll look at that in a second. Hold on. Just let me finish that thought. I'm still just wondering, coming back to the SIMD, why the signatures made it all the way down here after the variable length payload and not like here after the config values or something. I mean, that's also variable length. So is this, just the payload is even more. It's variable length within variable length. Maybe that's a great choice. Maybe that's a weird choice. If I would have designed it, I would have put those right here after the number of addresses before the actual addresses. Although to verify the signatures, you also need the addresses. So it would also be fine to put them right after the addresses or even right after the config values. And while we're there, might even put it after the instruction headers. It's still the same. Okay, yeah. But I would have put it before the instruction payloads. And to put those right after each other also makes sense. Doesn't matter. I mean, there is no best solution to anything anyway. It's always trade-offs. We keep talking about that. And that's apparently a trade-off that they accepted, that they now need to parse more to get to the actual signatures. Okay, cool. Now, we see so many bytes here, and I kind of want to look at that, but can I look at that more nicely? Look at this. This looks a little bit better now, easier to work with, because now we have 16 in each row. So, first byte, version, header, and what came after the header? Let's put the specification here. Version, header, and then 4 bytes of config mask. So in this configuration, the kit has put 0 actual config bits. So this is gonna fail heavily, even if DevNet would accept. But ignoring that for now, what comes next is the lifetime specifier. So that's this, a block hash, just random bytes. They don't say anything really. That's just a block hash that was just on DevNet. Then the number of instructions. We have 2 instructions, one to the compute budget program that will be ignored. And we have 4 accounts. Yes, 2 of them are read-only and 1 is a writable signer, which means 2 are writable. That's how you can calculate that. And then it's already addresses. Then we have 4 addresses. So we have 1, wait, does it check out? I think so. 2, oh, yeah. And then comes the system program. That's why 3, address 3 is all zeros. It's the system program. And then 4, that's the compute budget program. You know that because there is zeros here. That's the tailing ones that make the zeros. And after the addresses, we get the config values, which we don't have, so none of that. And then we already get the instruction headers. We had 2 instructions, so instruction header 1 with a call to the compute budget program, that's index 3, so it was the 4th account, which was the compute budget program. The next instruction is calling program with account index 2, which was the system program, but that was the first instruction. 0 is the number of instruction accounts, so this one takes 0 instructions, and then those 2 numbers that make up 1 U16 is the number of instruction bytes, because having just 255 would not be enough. Instruction data can be more than 255 bytes, so we need 2. Okay, so instruction data is actually 5 bytes. Does that make sense? Yeah, 1 for the instruction discriminator and 4 for the actual value. And that actual value should be in the config, which we don't have. And it will be actually somewhere back here. But first comes the header of the other instruction. Wait, this is the header. With calling the system program, having 2 accounts, so the payer and the receiver, those are the 2 accounts the system program transfer sol instruction takes. And 12 is the number of instruction data, How does that make sense? We have, I think, 4 bytes of instruction discriminator. Yeah, that checks out. And then the amount in Lamperts to transfer, which is 8 bytes. Yeah. That makes sense. Cool. So that's why we get to 12 bytes here. And then after the headers come the actual payloads with the account indices first. However, we said this instruction, the first one, doesn't take any accounts, so we have no accounts. So this one just gives instruction data and the length is 5, so 1, 2, 3, 4, 5. This is the instruction data for the compute budget instruction. It has instruction discriminator 2 and 44.1 is my 300. Does that make sense? 256. It's 256 plus 44. Yeah, that comes to 300. Perfect. That explains that. So that's the instruction data of the first instruction. Then comes accounts for the second instruction, because this one actually takes 2 accounts. So this and this one. First one, so my fee payer, is also the source for the transfer. And the second one, that's the recipient, a writable account. You know, we found it here. That's this one, whatever that account is. And it's just a random one that I generated. And after the accounts comes instruction data. Hold on, I think I'm missing something here though. My bad, I'm off by 1. That makes sense because I was confused, because that's already instruction data. That's already instruction data. We know that because 4 bytes for the instruction discriminator of the system program and 2 is this instruction discriminator for the transfer. Now it checks out. Yeah, that's already instruction data. So those 2 are that makes more sense because we start at index 0, so the fee payer is of course account 0, and then the writable account, the destination is 1. So why did I miscount here earlier? We said that is the header number 1 and that is the header number 2, and then was 5 bytes. 1, 2, 3, 4, 5. Yeah, that much was the instruction data of the first instruction. So the first 0 here is already an account index for the second instruction together with this one. Okay, and then we had 12 bytes of instruction data. So 4, 12. There we go. That's 12 bytes, the 2 for instruction discriminator, and this actually is the amounts of Lamperts that we transfer. And as an exercise, let's calculate that number, because we know it's little endian, so it's 0 times 1 plus, and now I get my calculator, 152 times 256, and then plus, and here I need to do brackets, 13 times 256 to the power of 2. So that's 65k something. That's the actual number. So 850,000 Lamperts is minimum balance for rent exemption. And we can quickly double check that. I mean, I'm close, but I'm off. What did I do wrong? Oh, we missed the plus. Plus that number. There we go. Then we get the right result. Yeah, then it's 890,000 Lamperts. And that's exactly that value. There we go. Now it checks out again. Okay, calculating that manually just as an exercise to prove that you understand it. But usually computers do that way better. So don't worry about it. Anyway, we know that those bytes are now the amount of Lamperts that we transferred, because that's part of the instruction data, which is part of the instruction payload. And then after all of that instruction payload come the actual signatures. So here we just have one signature that's 64 bytes for this one signature. So the signatures indeed come in the very end of the transaction in a version 1 transaction. Isn't that interesting? Okay. I mean, very nice. Good that we checked that out as well. I like to do it like this, looking at the actual bytes, so I understand what's happening. But now, should we first fix this or should we first send it? I would say let's first send it. Let's send that transaction to a validator that accepts it, because DevNet doesn't. So I guess we will need to start our own Solana test validator. Go to local and airdrop myself some sol. And then we're gonna change to local and run this again. and see what happens. Transaction simulation failed. That was kinda to be expected, but the reason is different. Transaction exceeds max loaded account's data size cap. Wait, but that means that my earlier assumption was wrong. Because look at such a transaction on DevNet. On DevNet, it's easy. Wait. If we look at such a V0 transaction on DevNet, then the total account size is 36 bytes. It used to display the bytes in this table. Explorer keeps changing. Because this is a 0-byte account. This is a 0-byte account. System program has 14 bytes though. And compute budget program also has 22 bytes. So each program will have some data length. So you will not be able to call a program. So the only thing literally that you can do is absolutely nothing. So if you were to do absolutely nothing, no instruction, could you then send this transaction? Still transaction simulation failed? No, transaction still exceeds max loaded account data size cap. Okay, then I take it back. Maybe it is taking all of the account into consideration, because now we literally have one account and my one account has 0 bytes, but that's not true because really it has 128. So let's test that. Let's make it work. But I actually have no idea how to do that. How do I set? It's not through compute budget instructions. I need to somehow do that with the kit. Okay, kit, what you got? Set something with max set transaction message. Here we're getting somewhere. Heap size. That's the fourth one, but I need the third one, which is loaded account data size limit. This one. So let's just check if I am correct with my assumption. Transaction message. If I put that here and then I run this. I love this. I love this. I should say there's no more error. There's no more error. There is just no more error. Did you see? Did you see that we just sent our first ever version 1 transaction? Amazing. That's cool. Because we now in here set the 1 bit for defining the max loaded account data size limit. That's bit number 4, I guess. 2 to the power of 4. Is that 8? Yeah, that makes sense. And that means, if we just quickly bring that back, the config is after the address. The address says there was the block hash. Number of instructions, 0. Number of addresses, 1. This is the address. And then look! The 128. That's the one that we specified here. And it's a 4-byte thing, so that's the entire number, but you know, we didn't use all the bytes. It's okay. So with that specification, we can actually send that transaction. Look at this. But now, more details, because now it's getting interesting for us. If we now bring back the instructions, it will now not work again. Can you tell me why? Just to use your brain a bit. Yes, see, I was correct in that it does not work. If you said, because we exceeded the max loaded account data size cap, then you are correct because you paid very good attention that this is actually the minimum that we needed, which I didn't even prove. Hold on, revert. With that, it does work, and with that, it should not work. No, it also works. So good that I'm testing this because I don't want to say wrong things. That's also still working. How much can I request that it still works? What is the limit then? There, so 1 is definitely not enough. 32 isn't either. 64 isn't either. Did I misremember how many bytes an account needs? Maybe I have wrong information in a previous video then. If 64 now checks out, yeah. So maybe the actual data of an account is just 64 bytes, which would make sense because what do we store? The address, the owner? No, we don't store the address. The owner, which is 32, Lampert, which is 8. And last time I calculated that through rent, right? Maybe rent has an extra 64. Let's do it again. That's for 0, and 64 would be this. Nice number. And if I do this minus this, then I still have half Yeah, that was my issue, right? So that's just half of that. So maybe rent for an account also takes into account 64 more bytes. That is not actually data of that account that we get as data, but that the validator still needs to store like something like the address of the account. That would make sense. So that's where my misconception came in, that an account's data, a 0 byte data account actually has 64 bytes, not 128. But you need to pay for 128 bytes of rent. Details! Told you it's a deep dive, such deep. And we can't stop here because we need to figure stuff out. Now, just to not have to deal with this, because the regular default was like 64 megabytes or whatever, I'm just gonna add a few zeros here and say, let's not worry about this, just to make sure we have enough for those. And then I'm gonna ask you again, okay, why is it this time gonna fail? Maybe it's not, but you tell me. To exercise your brain again, or to now actually show the thing that I would have expected that you told me earlier. Let's run this again. And it does not work as expected. Wonderful. And I absolutely love this. I so much love this, because the compute budget program where we request compute is telling me that we're out of compute. This is hilarious. I love it. This is great. This is absolutely comedical. Freaking amazing. Okay. Because it brings us to one very important thing for you as devs when you're working with a kit. Do not use set compute unit limit instructions, set priority instruction, all that stuff directly from the compute budget program. Don't use it with the kit, because the kit is smart, but it will let you break things, or it will let you do the thing that you want. If you want that instruction, it will give you that instruction. But the better way to do it is actually how we already saw it here. There is a set transaction message. Guess what? Compute unit limit. And with the transaction message function here, then the kit knows how to do it. So let's say I want my 300, which is even 150 too much if we don't need that. With that limit, now it should work. Look, it works. And now we're setting it in here. So we set the bit 4 and the bit 8, which makes it 12. That's the mask. We're setting those things. And the kit is doing that automatically. You don't have to worry about that. Kit takes care of it. And then that transaction goes through. And we could even do 150 here now, and it will still go through, because we're not paying for this one. And the funny thing is, if you put something here, even if it's, I don't know, even if it's 0, this is not taken anyway. We need to push that to 300 again though. This is ignored anyway, except you are now paying for compute. Check this. Oh, the default commitment is finalized now. Interesting. Transaction version 1 is not supported by the requesting client. Well, that's a whole other story of things are gonna break now once we have transaction v1. Okay, let's just maybe not. Never mind. Then I do something else. I shall simulate my transaction and log the simulation. Then, there we go, I get success, and extra units consumed is 300. But what did I want to say? You don't need this instruction. You could save yourself 150 compute and you still requested the same. It's not taken into consideration anyway. A transaction v1 ignores all the compute budget stuff. And so for devs, don't do it like that. Do it like this, because then it will put it in the right way. Because this way, look, if I do this at the v0, or even at the legacy, if I do that, then I also do need to set that here. Just need to import that. And then I can do a legacy transaction. I save that file. I am requesting 300. That transaction goes through. And what it actually did is it added a compute budget program instruction. Here, even at the bottom, so in the end. So you see that it's not the same as we had before. The kit added it in the back to request 300 compute units. Same code, but also works for different versions. I could also do version 0 here. But, haha, here we see it again. Because if I have a v0, now it has to request the compute budget program for doing those things, that additional thing, or both of them actually, cost me more compute. So once again, we see that with this strategy, I would need to increase that for it to work, but then it would also work here. And so we see the clear advantages that version 1 gives us. We can request fewer compute because we don't need to work with a compute budget program anymore. And that also means we don't need to put that as an account, so we save transaction space, and the entire transaction can be much bigger, which is another thing why transaction v1 is actually pretty cool. But I think I'm gonna save that for another video where we're gonna try and pack as much as we can in a transaction v1. I think it's good for today. We did send a transaction, look at that, just on local because the feature gate is not activated on any of the clusters yet. We do understand how our v1 transaction actually is serialized, and we had a look at the bytes and stuff. So I think I delivered all the things that I promised, probably even a little more here and there with some rabbit holes that I went into. So I would say I can leave it here. Transaction v1, pretty amazing development. I like this. We can do much bigger transactions now, and it's more efficient for the validators, which makes the whole network run more smoothly if everybody uses v1 transactions, which is not going to be the case, at least not initially. First of all, because there are a few issues. Number one, we saw some implementations might break now because you need to deserialize and serialize transaction v1 differently now. And if your client doesn't implement that, then it's just gonna crash because it thinks, oh, there's a signature, but no, that's actually the message. And then it's just gonna be confused. Or it doesn't support the v1 yet. So you need to make sure that your client support v1 transactions. And you should do that before the feature gate gets activated on mainnet. Second thing, address lookup tables are going away, which means you can't use ALTs anymore. If you depend on them, you gotta restructure. And there's probably another whole video that I'm gonna make just about that topic, address lookup tables versus v1 native with the trade-offs and everything. Because we said it before, we say it again, version 1 transactions do not have address lookup tables anymore. Which was just the big hack from the beginning, if you ask me. But we needed to quickly get something to work. So yeah. Overall though, transaction v1 is pretty nice. I enjoy it. Especially because we can now put more instruction data, bigger proofs, more addresses, more signatures into one single transaction. And you don't pay more for it, by the way. You pay for resources, and in the future, what you pay for exactly will also change. Yet another video that I need to make. But my first look at transaction v1, I'm actually pretty happy with it. This is cool. And also for regular people, nothing's gonna change, right? You can use a different version and then you have more space and whatever. It's a same. But for us devs and nerds, I kind of like it. I really enjoyed having a look at the individual bytes. For some reasons, I just like looking at that, but that's just me. I hope you enjoyed that too. If you did, give me a like and subscribe if you have not done that already. And then here are some other videos that you can watch. I will keep talking about transaction v1 in the future because it's a big change and it does change how we as devs operate and what we can do. Even though on the cluster, it's not different what we can do, but we can now put more things into one transaction, and that indirectly changes what we can do. So yeah, pretty cool.